Okay, let's look at problem 815 in the excuse me in the homework. This is a 120-pound cabinet is mounted on casters that can be locked to prevent their rotation, right? So the coefficient of static friction between the floor and each caster is 0.3. If H is 32 inches, determine the magnitude of the force P required to move the cabinet to the right if, and then you have three conditions, all casters are locked. Okay, I'm going to abbreviate that. That is four-wheel brakes, right? Part B, if the casters at B are locked, and the casters at A are free to rotate, in other words, front brakes. And C, if the casters at A are locked and the casters at B are free to rotate, or back brakes. Okay, so let's start with A. So for A, let's draw our free body diagram. So you have your free body diagram. Okay, you have the weight of this thing coming down. I'm going to call it weight. It's 120 pounds, but let's call it weight. We have some force P. Now we have forces here and here. I'm going to call this N, A, and N, B, the normal force at A and B. And then you have your friction at B and your friction at A. Okay, so that should be our free body diagram, and I'm thinking that's pretty much correct. So, just like many other problems, let's start with the sum of the forces, right? So sum of the forces in X equals 0. Wow, sorry. So in X we have, that's going to say that P is equal to F at A plus F at B. Okay, fair enough. And then we're going to say sum of the forces in Y equals 0. So that's going to tell us that weight is equal to NA plus NB. Okay, so right now we have too many unknowns. We got to kind of start consolidating down our unknowns. Well, we do know what F at A and FB are, right? We are looking for impending motion, the point just before it starts to move. So just before it starts to move, you have F at A is equal to NA times mu sub S. And F at B is equal to NB times mu sub S. So let's plug that back into this equation right here, okay? So therefore, P is equal to NA times mu sub S plus NB times mu sub S. So we can write that as mu sub S NA plus NB. Well, this is suspiciously similar to that. That is our weight. Therefore, P is equal to mu sub S times weight. So it's equal to 0.3 times 120, which is equal to 36. Okay, so P is 36 pounds. In other words, with all four wheels locked up, it's going to take 36 pounds of force to get this thing to move. Okay, that is the answer. Something that is not asked, but you should probably want to think about for a second is, does that actually work? Right? So now we're claiming that we need to push with 36 pounds of force right here to get this to move. Okay, you can imagine if this point and this point were not allowed to slide, and you start pushing this way, eventually you're going to tip the thing over, right? So let's think, okay, what is that point just before tipping over? Well, let's look at a free body diagram just before tipping, right? You have the weight coming down, you have this force P, so this is P, this is weight. Okay, so, and remember you have the normal and the friction, and you have the normal and the friction. This is B, A, B. Okay, but what do we know just before it tips over? Just before it tips over, this point right here comes off the ground, right? So if the normal at A is 0, the friction at A is going to be 0. So we're going to treat that point as if it's not there. We're going to call that is the moment just before it tips. So if these things are nailed to the floor, well, not nailed to the floor because that would, if they were not allowed to move forward regardless of the friction, they couldn't move forward. Then if you push hard enough, eventually this is going to lift up. So what is that magic number? Well, right now, let's take the sum of the moments at B is equal to 0. So you have P times your height, which is, oh, silly thing. Your height, I believe, is 32, given here, right? Plus, that is going to want to make it rotate in that direction. Weight's going to want to make it rotate in that direction. So I'm going to say this is equal to the weight times the distance of the weight, which is going to be half of 24, which is 12. So therefore, P is equal to 120 times 12 over 32. So P is equal to, it's 45 if I'm not mistaken. 45. So this thing, as it is, can handle up to 45 pounds before it tips over. Therefore, when we push at it with 36 pounds, your answer up here, P, then we know that it'll actually move and not tip over. So this part right here, this is unique to tipping. I'll even write that below it, tipping. And so we don't have to do this over and over and over. We just have to look at that once and say, therefore, it's good. Okay, so that is part A, if all casters are locked. What about part B? If the casters at B are locked and the casters at A are free to rotate. In other words, front brakes, right? So let's look at B. With front brakes, what do you have? You have this same block. You have the weight coming down here. You have a force P coming here. You have a normal force, normal at B. You have your normal at A. Now, these are rotating, so we don't have a friction at A, but we do have friction at B. Friction at B. Okay, so now that is our new free body diagram. So let's think of how to do this. It's, again, same basic idea. Let's say sum of the forces in X equals 0, and that's going to tell us that P is equal to F at B. So that's a pretty big deal. And sum of the forces at Y equals 0 is going to tell us that, again, NA plus NB is equal to weight. That's a B. Sorry, just got to trust me on that. Okay, what do we know about this force at B? Well, for impending motion, F at B is equal to NB times mu sub S. Okay, so what do we do next? We say, hey, we have some equations. What can we do with these equations? Well, we have how many unknowns? We have P as an unknown, and A is an unknown, and then B is an unknown. So weight, we know. This one is no longer an unknown because that is NB times mu sub S, which is, again, one of the unknowns. So we have 3 unknowns and 2 equations. So that's a problem. So we need a third equation. Well, what is a good third equation? So what would make sense for a third equation is taking the sum of the moments. And where should we take the sum of the moments? Let's say about this point right here. Again, you can do this in all sorts of different ways, but let's take the sum of the moments at A is equal to 0. So what's that going to tell us? P times H, which is 32, right, is going to want to make it rotate in this direction. This weight is also going to make it rotate in that direction. So plus weight times 12. And then this one is B is going to make it rotate in that direction. So equals NB times 24. And the friction at B passes through there. So therefore, it has 0 moment. Okay, so now we have 1 equation, 2 equations. So I'll put the 1, 2 equations, and 3 equations. So 3 equations, 3 unknowns, and we're off to the races. So since I'm looking for P, I'm going to look at one of these up here, and I'm going to say, you know what? I can solve that for P and so I can solve this for P, so therefore P is equal to, excuse me. So I'm going to go ahead and take the first and the third equation. I'm going to solve this for NB, right? So I'm going to, sorry for the mess, I'm going to say NB is equal to P over mu sub S, right? And so I'm going to plug that into this one here, and I'm going to say, therefore, P times 32 plus weight times 12 equals NB. So here I'm going to put P over mu sub S times 24. And therefore, I can solve that for P. It's just 1 equation, 1 unknown, and P ends up being equal to 30 pounds. So for part B, With the front brakes on, it takes you 30 pounds. So again, 30 is less than 36, so it doesn't take as much effort to push this thing forward with just the front brakes on, but it definitely takes more effort. But it takes pretty close to the same amount of effort, but it's still under this 45, so we're not going to tip over. Okay. So now let's look at part C. Now part C, we're looking at the casters at A. In other words, rear brakes is what we're looking at part C. So I'm going to put this over here. Sorry for the mess. C. You have the same block. You have the weight coming down. You have a P coming there. Here you have normal at A and a friction at A, and you have a normal at B, but no friction because it is moving, or it is free to move. Okay, so again, same deal. Sum of the forces in Y equals 0 tells you that weight is equal to NA plus NB, so that hasn't changed. Sum of the forces at NX equals 0 is going to tell you that P is equal to FA, which is NA times mu sub S for impending motion. So again, that's only true for impending motion right before it moves. And then I can say, well, let's take the sum of the moments at B is equal to 0. So let's take some of these moments right here. And so you're going to end up with P times the height, which is 32, plus NA times 24 is equal to the weight times 12. So if we solve this for NA just for giggles, we'll say NA is equal to 12 times the weight minus P times 32, all that over 24. Then plug that into that equation just like we did over here, right? And you end up with P of 12.86 pounds. Okay, so let's do some sanity checks. What do we have? With all four wheels hitting the brakes, we have, or all two wheels hitting the brakes, it takes 36 pounds of force to overcome it, which is less than our tipping force, so we're good to go. Now, part B, with just the front wheels hitting the brakes. Okay, with the front wheels hitting the brakes, it takes 30 pounds of force to get it to move. So not as much as 36, but still pretty good, and still less than tipping. With just the back wheels, it takes 12.86 pounds to get it moving. So this is why, in a car, on a bicycle, anything, the front brakes are really what's doing a lot of the work. The back brakes, if you just hit the back brakes, you just don't have the stopping power as you do with the front brakes. And then better yet, you hit all four brakes, or the front and back brakes, and then you have the most stopping power available. And that's this problem.